So let's apply some of the information that you've gotten in the previous videos on NMR spectroscopy towards a problem where you're given the mass percent information in an NMR spectrum, and your goal is to determine the structure of the compound. So first, let's just go over some of the data. Here are the mass percent data. It's 64.82% carbon, 13.6% hydrogen, and 21.59% oxygen. It has a mass to charge ratio, a molar mass essentially from the mass spectrum of 74.07. Here's the NMR spectrum. Let's break that down a little bit. There are 1, 2, 3, 4, 5 sets of peaks in this structure. We have a triplet here with 3 hydrogens, a doublet with 3 hydrogens, a multiplet with 2, a singlet with 1, and a singlet with 1 and a multiplet with 1 hydrogen. The first thing that you're going to want to do, and this is true of almost any sort of structure determination problem, whether it be IR, NMR, spectra, or mass spec, you want to figure out what the formula is, and you want to figure out the degrees of unsaturation. Because the degrees of unsaturation, if you remember, tell us about the number of bonds, or double bonds, or rings that you can find, or triple bonds, or rings that you can find in a structure. And for every degree of unsaturation, you have one of those features added. And if you have 2 degrees of saturation, you have 2 double bonds, or a triple bond, or a ring and a double bond, that kind of stuff. Okay, so let's go ahead and do the formula, or go over how you do the formula again. You may have to review some Gen Chem, but remember, if you assume that you had a 100-gram sample, then each one of these percentages would represent the number of grams. So if you take the number of grams of a compound, you divide by its molar mass, the grams per mole. That tells you how many moles are in that 100-gram sample. And you go do that for carbon, hydrogen, and oxygen. And what you find is you get these 5.4, 13.49, and 1.35. And then the next step is to convert those into whole numbers by dividing by the lowest. So I divide by the 1.35, dividing by smallest, I get 4 carbons, 10 hydrogens, and 1 oxygen. So my formula is C4H10 and O. Then the next thing you want to do is to figure out the degrees of unsaturation. Now for a hydrocarbon containing oxygen, all you have to do is follow the 2n plus 2 rule. That is, if you have 4 carbons, you'd expect there to be 10 hydrogens. And this has 10 hydrogens, and since it has the number of hydrogens you expect, the degrees of unsaturation is 0. And then for every 2 hydrogens, that's 1 degree of unsaturation. And we'll cover other elements and compounds as we go along, in the compounds as we go along. Okay, so what do we do with this information? Well, what I find the simplest thing to do is to translate these integration values into structural components. So you know there's 3 hydrogens on this grouping. Now I have 3 and 3, that's 6, and 2, 8, and then 2 more is 10. So this represents, notice this C4H10, this represents all the hydrogens in the compound. It's very likely that when you have 3, that's a methyl group. When you have 2, that's a methylene, a CH2 group. And a 1 is a single hydrogen, whether that be on the alcohol or it's on a carbon. So let me put these together for you, okay? So here's my spectrum, and this is what I did. I just made bits of the molecule, and now we're going to put it together. So remember, the multiplet means it has many, many neighbors. The singlet means it has no neighbors. And the only kinds of things that really show that are alcohols, or that is a singlet with 1 hydrogen, are alcohols, or occasionally when you have like alkenes with lots of degrees of substitution, anything with lots of degrees of substitution on it, where there's a single hydrogen on there. That's where you expect that kind of thing. We don't have any double bonds, but it is possible that we could have more degrees of substitution. So let's go ahead and look at this, how this might come together. So let me put this in the middle. It has the most available things to bond with, and I'm going to put this next to it. And ignore the red squares. It's a drawing program for structures. It doesn't like the bonds laying on each other. So how does this help us? How does this structure correspond to some of this data? Remember, an oxygen's electron withdrawing group. So this carbon with the oxygen on it, you'd expect this hydrogen to be shifted downfield. If you remember, that shift for an alcohol is typically, that is a carbon with an alcohol on it. The hydrogens on that carbon are shifted around 2 to 2.5 parts per million. Typically it's around 2. So if you think about a methylene group, typically starting around 1.5, this hydrogen starting around 1.5, then, or methine group starting at 1.5, then this oxygen shifted around 3.5. So that explains this one. It doesn't explain the multiplicity, all the peaks that you see, but it explains where this is. This singlet is most clearly the alcohol, and then we have to add these other groups. Now, the methyl groups, when you have methyl groups, the nice thing about methyl groups is they have to go on the end, so that means this has to go in the middle. Okay, and then there's only 2 places left. I can put it here, and I can put it here. Okay, so now I got to rotate this, and I'll put these guys together. So let's see how the data verifies this particular structure. I have a methyl group. It's twice removed from the electronegative oxygen, so you expect the methyl group to be where you expect to find methyl groups that have no electron withdrawing groups nearby, and that's around 0.9 parts per million. So that's here. It's a triplet, which means, using the rule of neighbors, that I have 2 neighbors. That is, if you think about the gaps in here, there's 2 gaps in here. There should be 2 neighboring hydrogens on the adjacent carbon. There's a hydrogen here and a hydrogen here. So these are the 2 neighbors. That explains both the triplet and the integration value of 3. This is a doublet, and it's around 1.2. Now this is also a methyl group, but remember, it's adjacent to the carbon with the electron withdrawing group, so this is shifted downfield. About 0.2 is what it looks like. So that's in this position here. It only has it's only a doublet rather than this being like a triplet, because there's only 1 hydrogen here next to this to cause the splitting. We called it coupling, if you remember from the earlier lectures. So this is coupled, and it produces 2. And then if you look at this carbon is also 1 away from this electronegative group. It's a methylene group, though. So methylene groups typically start around 1.2. If the methyl group, which is 1 away, shifted about 0.2, you'd expect this to shift about 0.2 to about 1.4. So I got a 1.4. This is around 1.2. This is about 0.9. This is typically around 3.5, and this one is quite variable. It depends on the structure, but for alcohols I typically find it is between 2 and 3 somewhere. So this structure is verified by this spectrum and vice versa.